On today's World Insight, scientific diplomacy, how scientists of all disciplines around the world put their minds together toward fixing humanity's greatest challenges. On this, we'll hear from a top theoretical physicist and an accomplished mathematician in today's special series, Brilliant Minds, as we pick the brains of Nobel laureate in physics David Gross and Fields Medal awardee Shing-Tung Yau, the chairman of the International Congress of Basic Sciences.
Hello and welcome to World Insight with me, Tian Wei, and this is our special interview series, Brilliant Minds. Basic sciences are the building blocks of scientific advances. Not only that, some outstanding scientists are also shouldering great responsibilities in informing the society. On the sideline of the ongoing International Congress of Basic Science in Beijing, I sat down with Professor David Jonathan Gross, a Nobel laureate, a preeminent figure in the theoretical physics, whose contributions have profoundly shaped our understanding of fundamental forces of nature. He is known for revolutionizing the general understanding of quantum field theories. But in our conversation, he gave a lot of thoughts on how nuclear development should be used for peace and prosperity, not antagonism and conflicts. Your research actually help us better to understand, because quantum and gravitational waves, all these are trying to help the humankind to understand the universe much better.
Well, my generation was lucky enough to live at a time where we developed a really very good theory of matter and forces. And that actually made it possible for us to understand the universe based on what we observe, but take it back in time to when it was very small, the observable universe very small, very hot, very dense. We can't do that directly, but using the theory, the understanding of what happens to the forces in nature when we go to a very hot and dense situation, astrophysicists, cosmologists, and particle physicists have been able to understand the complete history of the universe from the very earliest possible times till today. One of my friends said that the discovery for which I got the Nobel Prize led to the understanding of the strong nuclear force, changed the universe from the early universe from a hadron or nuclear hell, theoretically, to a quark-gluon heaven. So it enabled us to really calculate and trace the universe back to the very beginning. Then everything breaks down and we don't know what's going on. But without the basic understanding of particle physics, what we're made out of and how it works, we really would not have been able, as we have succeeded more or less, we think, to understand the complete history of the universe from the beginning, which we don't understand, till today and beyond.
Did you realize that actually it is an unprecedented way that you have paved for actually many of us these days to understand the universe much better?
Well, not that far, but it was clear with the discovery that we made that we could understand the strong nuclear force, which before that was a complete mystery. And suddenly everything fell into place. And yeah, it was a very exciting feeling. There were many problems, but somehow it all fit together. And many of my colleagues, not all of them, actually a small number, understood that as well. I call them the smart people. But many people said, oh yes, but how can you have a theory of quarks and never seen a quark and never will? Doesn't make sense. It took many years to be recognized, say, by prize committees, or to be sure that they're right. Because in science in general, and certainly in physics, the only judge of ideas, of theories, is nature.
When your research, as terrific and significant as it was not recognized, what was it like for you?
No, it was recognized by the smart people.
Yes, by the smart people.
And by a growing number of people. So one of the awardees this year was Shing-Tung. 1 year after QCD, the theory of the strong interaction, nuclear force, he and a group in Stanford discovered a particle which had very unusual properties, but was kind of predicted by the standard model, although at that time, theorists weren't taken very seriously because they'd been so unsuccessful for so many years. But that discovery just fit beautifully within our understanding of the nuclear force. And that so-called November Revolution convinced many people that this was the right theory. But it took really at least 20 years, if not 30 years, to be convinced. You have to ask nature, am I right? How do you do that? You make predictions of new phenomena or new measurements that nobody's ever done. And usually nature says wrong, wrong, wrong. Sometimes it says not wrong. It never says right. And if it does so over and over again for many years, that becomes accepted knowledge and appears in high school textbooks. But it's a long process.
It is.
So the experimentalists who discovered the J-psi particle won a Nobel Prize 2 years after the discovery. They discover it, it's there, 2 experiments, they agree. That's, in the case of the Higgs particle, an essential part of the standard theory that we have, it took 50 years between when the theorist proposed this essential element of the theory to when it was finally discovered 10 years ago.
So what does that mean, that time difference? That you discover something that you are confident about and your smart people friends certainly were very excited about, to the time when people realize, even the Nobel Prize committee realize, this is treasure.
It's a continuous transition for theoretical advances. Because as I said, it takes, there's no way of proving a theory is correct. And by the way, of course, all scientists, especially physicists, realize that no theory is going to be correct forever. Einstein knew very well that his theory of gravity is provisional and will change. And he spent years unsuccessfully trying to change it, his own theory. So the history of physics teaches us that all of our concepts even, our theories, are provisional. All of science is provisional. That's one of the problems with informing the public, as well as governments and politicians, about the findings of science. Because they want certainty. They want to be told, this is the way it is. And all we can do is say, we have a good theory, a good model, and based on the data we have and the understanding, it looks very much like this with some probability. But there's some uncertainty. Our data isn't perfect, our understanding isn't perfect, it could change. But people get very upset when scientists come back later and say, well, our original understanding of COVID was slightly wrong, and we made mistakes in telling you how to behave. And then science loses. Then people begin not to believe anything that scientists says. This is very silly. We actually need to educate the public as to what science really is and what knowledge really is. There is always uncertainty.
But people are being rhetorically educated about the world is like either A or B, black or white. And we are seeing that even more.
Yeah.
That's where ignorance, arrogance all come from.
In science, especially in physics, we came up 400 years ago with a very good method about how to proceed. We base our understanding on observation of the world, on experiments that test our ideas, and on mathematical theories that form the expression of our knowledge and allow us to make predictions and control nature. That method, and not to make assumptions based on religion or politics, but only on knowledge that's acquired by this method, with the understanding that it's bound to have problems and be improved. In physics, there have been many revolutions, each one improving and extending our understanding, explaining why the previous knowledge was correct, but slightly wrong. If you understand that method correctly, then you have a better guide to action based on knowledge, and all other methods, especially those governed by politics or religion, really don't work. But people much prefer to be told, this is the way it is, as opposed to, this is the way it seems to be, pretty good accuracy, we can tell you what it is and make predictions. But you should always question our assumptions, you should question our theories, and test them.
The bubbles people build for themselves, that they only believe and want to listen to and only interact with the people that belong to their own group, so to speak. And this bubble is getting ever more, that we are not really listening to each other that much.
It's awful. Especially science, and impact on science, because in scientific culture, we treasure disagreements, arguments, competition between ideas, where the judge is nature and not power or force or superstition. So one thing are the bubbles you're talking about, the political bubbles over allocation of resources or overuse of power. But the other thing are the bubbles that are being established by governments now in countries between different scientists. Now, science is universal. The laws of science, of physics, apply everywhere in the universe, not to speak of the Earth. We all are asking the same questions, and we benefit enormously from collaboration, cooperation, discussion. So the increasing attempts to isolate people because of industrial secrets and military conflicts is very detrimental to the development of science and, of course, to the international harmony. Very disturbing. Over the years, been going often to China is to try to increase the collaboration, cooperation, and discussion, openness in the scientific level between our two countries, and which has been marvelously successful and beneficial to everyone. And the movement in the last few years in the opposite direction is very disturbing to me. One needs to resist.
We are seeing a widespread of nuclear technology, especially for nuclear weapons.
Oh, yeah.
And the latest geopolitical situation is only going to speed up that process, because countries realize only when they have it, they're safer, quote unquote, as a result of the latest events. So, Professor, how can you persuade others that it is not in their interest to have these widespread nuclear weapons?
You know, when I grew up as a child, during the Cold War, we were taught in school what to do when the bombers came and dropped nuclear weapons, how to get under the desk and protect ourselves, which was nonsense. But we were scared. And until the end of the Cold War between the United States and the Soviet Union, everyone was terrified of nuclear war. For good reason. We came very close, much closer than anyone realized until recently, when all the facts have come out, to nuclear war. And we have come very close many times. And we're now closer than ever.
But at that time, there was mechanism being established as a result of fear that there will be real nuclear war. But the question now is, we don't have those mechanisms anymore, or those mechanisms being thrown out of the window.
When there were two superpowers fighting each other or threatening to fight each other, the governments would use that fear to mobilize support for their side of the war. But once that ended, every government in the world tries very hard not to inform its citizens about the dangers. And I've been shocked recently, as I get more and more worried, talking to young people. So my theorem is that anyone below the age of 40 knows nothing about the danger, about the facts, and is not worried. The leaders of all of our countries are as scared as I am. They know the facts. But they don't know a solution. And events in a chaotic, fragment world are moving in the opposite directions. But they don't have much incentive to do anything about it. They don't, because nobody's asking them to.
So can China and the United States do something about this
Of course,
together?
If the people of the world realize the unbelievable danger and demand in some way, or request from their governments, whose leaders know exactly how dangerous it is. They're not unaware of the danger. It's not like climate. This is a man-made danger, can be reversed, and they know what the danger is.
How do you see these interactions among scientists could provide at least some hope about the possibilities that we can still work together?
Well, that was always the great hope and part of the selling point for open exchanges between countries. And it's correct, absolutely correct. And it's worked very well, especially between the United States and China. It's always been a hope of scientists with the international connections that they could serve as a bridge between different countries. It's called scientific diplomacy.
My exclusive interview with David Jonathan Gross, Nobel laureate in physics, on what kind of future scientists want to see and how they can contribute. And this is World Insight, still to come in the program. High-profile Brilliant Minds interview series. How far can scientific cooperation go despite complicated geopolitics? Professor Shing-Tung Yau, Fields Medalist and Chair of the International Congress of Basic Science. Next. Welcome back. This is World Insight with me, Tian Wei, and this is our high-profile interview series, Brilliant Minds. He is one of the greatest mathematicians of our time, Professor Shing-Tung Yau, the first Chinese recipient of the Fields Medal, often called the Nobel Prize for Mathematics. His groundbreaking work has not only reshaped the geometry, but also laid the mathematical foundation for string theory in physics. Professor Yau has long been committed to nurturing talent, advocating for scientific rigor and innovation. In recent years, he has been devoting himself to the academic exchanges among basic scientists by chairing the International Congress of Basic Science. He told me that amid all the changes, he and other scientists should remain what he calls thick-skinned and hard-boned in order to weather the headwinds and make sure science is the connector to bring people together. In your opening speech at the Congress, you talk about this soaring of new theories as well as applications in many of these areas that your International Congress of Basic Science covers. Can you explain more as to what this means for scientists?
Oh, well, we explained there already. Physics provides us nature, what they see from experiment and all that, but they are not sure what they see can be explained in physical theory completely. They need mathematics to help, and mathematics is very rigorous. Once we verify some theory is right, and it will be extremely important for the future experimentalists to follow. And well, it promotes the theory, and the theory could be wrong if the experiment come out to contradict it, then it's probably due to some assumption that they make is not quite accurate. Mathematics is always right. It's just that the assumption may be wrong, and we need to improve it. And in this way, gradually, we understand nature much better. The theory got upgraded, and then experiment got onto some new directions and all that. But in this whole process, technology is very important. Technology, given a computer, you know what the machine can do for you. By hand, we cannot calculate everything. Mathematics could do something, but up to some extent, we still need computer to help. But computer cannot be perfect because they make mistakes if they just keep on running in this way, and we need mathematics to help. So 3 different subjects help each other, and we make progress together. And I think it's an exciting time because all these fields are making big progress.
Yes.
And the younger people are excited about it.
Now, in mathematics, some younger generations are already making great achievements and be able to solve some of the earlier long-lasting problems, including some of your students, in fact, or people who work with you very closely. Tell me more about where they are and why do you think this is so important? Because you have been advocates for them.
Well, I think more in terms of modern mathematics, China starts around 19th century and start to learn. And then the major first step, I would say, starts around the early 20th century. So I would say it's like running a 400 relay.
400 meters relay.
Relay. So I would say the first 100 starts from Professor Chen, my teacher, in the 1930s, and there are several other people in that group among the Chinese. There are Wei Liangzhao and several very outstanding people. And then in this, I would say in the second generation, kind of many friends of mine and myself following their footsteps and getting the second part. And then the third part is starting like my students and some of the young generation like Hong Wang, that you know, and then there's Dan Yu, and then Zhang Wei, and in many different, in number field and all that. So this generation are doing very well. The third relay is doing excellent well, I would say, at this moment, happening at this moment. They are close to getting fused metal, which we had some difficulty before for students growing up in China, mainland China. But now we are watching for the last relay, which we think it should be accomplished in the next 5 to 10 years.
Yes.
That's how I look at it.
Science is really taking off, basic science, but at the same time, geopolitics also has been changing. How do you, as a scientist, look at these things and how thick skin and hard bones you have to have in order to let platforms like these, where you bring all the basic scientists, well-known ones, together?
This is very important. We have to open up no matter what. And basic science is always fundamental to...
When you say we, meaning China or meaning
China,
Congress or?
Well, the Congress is one of them, and the Congress, part of China, of course, is an important gateway for China to open up to the Western world and to see our friends from Europe, from America, which with the current situation, it could be difficult if we just send our students outside because we are being blockaded by American government and all that. But science should have no boundary, and all scientists knows that, and they know they can learn from us, and we of course learn a great deal from them, and this is a very important bridge. And we learn from each other. Without learning from each other, science would progress much slower. And especially for China, we cannot close up. We have closed up the gate for a few hundred years. That was a disaster for Chinese development in science. So we should insist to open up. I should mention an interesting curiosity. You know, Japan, of course, during the Second World War, has invaded many countries. But even during the war, some of the Japanese scientists are doing really great, important work. And they are not necessarily related to weapons. And some very fundamental work was performed, even during the war period. And they also try to learn from outside. So
there are independent thinking scientists.
Yeah, they are independent thinking. So science is a very attractive subject to many human beings. So we are attracted by its beauty, and the truth transcends war, transcends nations, and I believe this is very important.
Professor Shing-Tung Yau, an outstanding mathematician and also chair of the International Congress of Basic Science. That's all the time we have for today. If you'd like to know more, search World Insight. Check out our YouTube channel, follow us on X and Facebook. I'm Tian Wei on behalf of my team. Thanks for being with us, and I'll see you tomorrow. Bye for now.